Good day, dear colleagues. First of all, I would like to thank the organizers for inviting me here. It's a great pleasure to make a talk here. And this is my presentation, but the main message of my talk was about a closely connection between combinatorial optimization and learning theory. These two areas of the modern computer science appears to be very, very close. As we know, many machine learning problems obtained in machine learning, such as pack learning, boosting, cluster analysis, etc., continuously presenting the new challenge for designers or new optimization methods. And any time when we can reduce the learning problem to the appropriate combinatorial optimization problem, such as max-cut, k-means, p-median, TSP, etc. Anytime when we can obtain the good approximation in this combinatorial optimization problem, we can obtain new ideas to construct new efficient learning algorithms. But there are the inverse way to collaborate to these two fields. And my presentation about this inverse way. We can consider some examples. I stop on two examples in this small talk. When the learning techniques can be efficiently used in producing the approximation algorithms in combinatorial optimization. And the first example is rather classic. It's about the well-known set cover and hit inside problems. And the second one is about our own results, which are about piecewise linear committee classifiers and so-called minimum affine separating committee, which minimize VC dimension in the class of such classifiers. And that's all. OK. I start with small definitions, the very well-known combinatorial optimization problems that they are definitely equivalent to each other. First of them is defined as follows. Input a finite range space or maybe hypergraph or just a family of subsets. Find a ground set X, and R is a set of hyper H subsets of X. And it's required to find the smallest cover, R1, Rs, of covering all the ground set. And the equivalent formulation, equivalent statement, is known as hitting set. On the same hypergraph XR, we should to find the minimum capacity subset, which has a non-empty intersection with each hyper H from R capital. It's really easy to say, to see that these problems are equivalent and they are on dual to each other. For example, if the instance of set cover problem is defined by such incidence matrix, here to find a cover, we just should to find the smallest number of rows covering all the columns in this matrix. If we transpose this matrix, we just consider a corresponding instance with a hidden set. The both problems are well-known combinatorial optimization problems. They are NP-hard. And the hidden set problem remains intractable even in the case when every point of ground set is covered by exactly two subsets R. It's vertex cover problem. What about approximation algorithms? First of them is the famous Johnson's greedy algorithm, where we just should iteratively add to the building color the currently biggest subset, which has the biggest intersection with the uncovered subset of ground set. And the other one is Low's linear relaxation algorithm, when we reduce the initial integer program to the corresponding LP relaxation program. And after getting the solution of this problem, just round the obtained fractional solution appropriately. Both algorithms are good, but have very poor approximation ratio, which depends logarithmically on size of the ground set. It's curious that Johnson in 1970s proved the tightness of the obtained bound for his algorithm, and he proposed the infinite sequence of examples of instances of the set cover problem. To give such an instance, we just fix natural number p and consider ground set of such size. And the point in this example, p is equal to 3, and ground set is just depicted by these points, and subsets is just rectangles. And it's easy to see that optimal solution in this example is just equal to 2. We just have to take these two rectangles horizontal, but the greedy algorithm gives us very pure approximate solution with such number of rectangles. And that is a proof of tightness of this, this bound. But good news was obtained by Uriel Feige in 1998, which proved that set cover cannot be approximated rather good if p unless p equals np. So the Johnson's algorithm are best one up to the some fixed factor, but as the previous speaker, I asked a question: if we need the better approximation, and in this case we just need some new for combinatorial optimization and old for machine learning techniques, which based on finite VC dimension and just boosting. Let's see. So in the general case of the problem errors, we cannot make a good approximation, but unless p equals np. But in real life applications, for example, wireless sensor cover problem and something else problem can be appear to be very, very special. Very more special. Maybe in some special cases we can get much better approximation. And the hint to consider spaces, to consider hypergraphs of finite VC dimension and boosting-like optimization procedures. Just some definitions. First of them is follows the well-known definition proposed by Professor Vapnik, but in combinatorial optimization it's proposed by Hostler and Wales. So let hypergraph XR be a finite hypergraph, and the subset N is called epsilon net for R if it intersects every efficiently large subset R of our hypergraph. And this concept can be easily extended to the case of weighted sets, and it can be done like this. We just fixed some measure, non-negative measure on power set, and just we require that epsilon net intersects with any subset R which has a weight, no small weight. Okay. The other 2 points is just 2 oracles. First of them we call netfinder. It is just an algorithm which for any accuracy epsilon and for any measure can find an epsilon net of such a size. And the second one is called verifier. and this algorithm for any approximation h just states either h is the solution of our problem, is a hidden set, or it returns an non-empty subset R, such R intersects H is equals to empty set. And the next point is just boosting. But boosting is, like the boost algorithm, is just a simple specification of the well-known multiplicative weight update algorithm. And in our case, it works as follows. Assume we know the optimal value of our problem. Denote it C. Initialize the uniform measure on the ground set, and after that, iteratively repeat the following steps. Using the first oracle, find such an epsilon net of such a size, and after that, use your verifier and check it for the optimality. If it's optimal, then stop, and otherwise, take the subset R proposed by the verifier and just double all weights of all points belonging to this subset. And after that, return to step 2. The main theorem was proved by Broniman and Goodrich in 1995. If the optimal solution of our hidden set problem is equal to C, this algorithm is just algorithm this algorithm is like to add a boost algorithm, you can see. So this algorithm iterates at most such times, and the total weight will not exceed this constant when n is size of x. And I skip the proof, it's very simple. What about accuracy and complexity bound? Complexity bound is like this. At any iteration, we just call one any oracle, first and the second one. And what about approximation ratio? This approximation ratio can be achieved much more better than logarithmic approximation ratio if we fixed the VC dimension. So what is VC dimension? It's very familiar definition, but now we use it in computational geometry and in combinatorial optimization. So first, a subset Y of the ground set is called shattered, is shattered by the set of family of subset if a factor set produced by this subset in the family of R is equal to power set of Y. And it's easy to show that any singleton is shattered by the subset R. And the number D is called VC dimension of our space if it's equal to the largest shattered subset Y. And that is all. So let our hypergraph has a finite VC dimension thanks to Professor Vapnik. So in this case, this algorithm, which we showed in the previous slide, can find the epsilon net and the solution of our problem of such a size. And as a consequence, we have an approximation algorithm with such an approximation ratio. Not logarithm on n, but d of logarithm dc, when d is VC dimension, c, and c is an optimal solution. So in that example, which I mentioned some slides ago, our algorithm can obtain the approximate solution with finite approximation guarantee, fixed approximation guarantee. It's very, very well. So what about our own results? I will be very short because I have very short time slot. So we consider the committee decision rules. Committee decision rules of affine functions For example, if we have a finite sequence of affine functions and we combine their decisions just using a simple loading, then this aggregated decision rule is called committee or committee machine, maybe. And if we require that this committee rule is correct on the given sample, then this sequence F1 and F2 is called affine committee separating the sets A and B. And it's easy to verify that to minimize the VC dimension of such committee rules, we should to find committees with minimum number Q. And the corresponding combinatorial optimization problem is minimum affine separating committee problem. OK. And some example. In this case, the dimension of the space is equal to 2. We have a training sample of the exemplars of the first class and the second one. And in this case, we can construct an same piecewise linear committee decision rule containing only 3 members. OK, what about complexity and approximation results? Complexity. This problem is NP-hard in the strong sense and remains intractable even in this simple case. And this problem, like MASC-GP problem, is hardly to approximate unless P equals NP. Namely, there are no polynomial time approximation algorithms with such approximation ratio, unless P equals NP. What about approximation algorithms? The best one for the next date was the approximation algorithm proposed in 1970s by Professor Mazurov, and this algorithm is has linear running time and such very poor approximation ratio. But when we fixed the dimensionality of the space, we can approximate our problem rather better with such approximation ratio. And finally, if we use the multiple weight update algorithm like this we considered some slides ago, we can significantly improve such a bound like this, and this is a finite result. So I'm going to conclusion that learning theory and combinatorial optimization are really closely related. Using some learning theory techniques admits us to develop new polynomial time approximation algorithms with record state-of-the-art approximation guarantees. And some reference publications. First of them belongs to Professor Vapnik, Theory, Probability and Application, 1971. Here, this VC dimension was first maybe proposed some papers, and our results you can find in machine learning this year. So, thank you very much.